Aligning a large language model through traditional reinforcement learning from human feedback requires an enormous supply chain of human labor. To train a model to recognize and avoid toxic, dangerous, or offensive outputs, developers collect tens of thousands of human comparison labels. Every label requires a person to read a malicious prompt, evaluate two model responses, and rank which one is safer. This process creates a scalability problem and inflicts a severe human cost. Beyond the financial expense, the work causes psychological trauma for people tasked with reading adversarial, hate-filled red teaming prompts day after day. Human labeling also introduces a behavioral flaw. When faced with sensitive prompts, human annotators predictably reward canned refusals, phrases like "I cannot answer that," because a blanket refusal is universally safe to approve. This implicit bias trains the AI to be evasive. Instead of establishing helpful boundaries or explaining why a request is inappropriate, the model learns to shut down engagement at the first sign of controversy. Standard RLHF presents developers with a false choice, trading away model helpfulness and conversational transparency for an opaque, unscalable version of safety. In 2022, researchers at Anthropic published a framework called Constitutional AI, designed to eliminate human harmlessness annotators from the alignment loop. Their thesis is that we can align models by feeding them explicit natural language rules, a constitution of 16 specific principles, rather than relying on these subjective gut feelings of crowd workers. These principles form 4 distinct groups: identifying general harms and ethical breaches, evaluating discrimination, dictating tone, and requiring thoughtful explanations over refusals. The architecture relies on a 2-phase pipeline. It begins with supervised learning from AI critiques, or SL-CAI, and then moves into reinforcement learning from AI feedback, known as RLAIF. By encoding alignment goals as auditable text prompts, constitutional AI transforms subjective human safety into a deterministic, self-improving algorithmic loop. Before we can optimize a policy with reinforcement learning, we have to put the model in a safe distribution using supervised fine-tuning. We start by feeding an adversarial prompt into an unaligned, helpful-only baseline model. Because this baseline model has no safety guardrails, its initial sampling generates a toxic or unsafe response. This triggers the critique step. The system randomly samples one of the 16 constitutional principles and forces the model to evaluate its own toxic output against that specific rule. In the revision step, the model is prompted to rewrite its response, explicitly addressing the self-identified violations in its own critique. This critique and revision sequence repeats, drawing on different principles, covering all facets of harmlessness. Finally, the baseline model undergoes supervised fine-tuning. We apply standard autoregressive cross-entropy loss over these final prompt revision pairs to update the model parameters. This supervised loop serves as an initialization phase, forcing the model to articulate explicit violations before rewriting the text creates a safer baseline than simply asking it to rewrite the response directly. Supervised fine-tuning provides the initialization, but peak alignment requires reinforcement learning. In this phase, the newly trained SL-CAI model processes a fresh red teaming prompt and generates 2 distinct candidate responses. Instead of humans ranking these pairs, an independent language model acts as the evaluator. This is the feedback model. The feedback model evaluates the 2 candidates as a multiple-choice question, asking which response is less harmful under the sampled constitutional principle. To calculate the preference, we extract the normalized log probabilities for the output tokens corresponding to choice A and choice B. This produces a precise mathematical preference target. This multiple-choice extraction is the core innovation of RLAIF. It converts raw text generation into a continuous numerical preference signal, bypassing the human labeling bottleneck. There is a constraint here. To provide accurate evaluations, the feedback model must use step-by-step chain-of-thought reasoning. This scatter plot shows the mathematical consequence of chain of thought. Reasoning step-by-step makes the model overconfident, snapping its preference targets to extreme binary values of exactly 0 or 1. Feeding these uncalibrated, extreme targets into a reward model causes instability and gradient explosions during reinforcement learning. The engineering fix is COT probability clamping. Precise. The raw preference target is mathematically clipped. Any value outside the boundaries of 0.4 and 0.6 is squashed flat, forcing all extreme confidences into a stable horizontal band. This clamped soft target is fed into a cross-entropy Bradley-Terry preference loss, training a stable hybrid reward model. The pipeline concludes by running proximal policy optimization. This process fine-tunes the final policy directly against the stable reward model, while a KL divergence penalty ensures it remains anchored to the baseline. Probability clamping is the mathematical linchpin of RLAIF. Without it, AI self-reflection devolves into reward hacking, destroying the alignment process. This graph charts the empirical results, mapping the trade-off between harmlessness on the x-axis and helpfulness on the y-axis. The standard helpful RLHF baseline scores high on helpfulness, but fails on harmlessness, readily answering dangerous requests. When we apply human feedback, harmlessness improves, but helpfulness plummets because labelers reward evasive refusals. But the constitutional AI model with chain of thought breaks this curve. It matches human harmlessness while maintaining superior helpfulness, reshaping the Pareto frontier. This happens because the Constitution explicitly instructs the model to engage constructively. Instead, it replaces canned evasiveness with thoughtful explanations of its safety boundaries. The evidence shows AI feedback outperforms human feedback. Governing models with explicit rules yields demonstrably better behavioral outcomes than relying on the instincts of crowd workers. This architecture has a physical limitation. RLAIF has a massive model-scale dependency. Models under 52 billion parameters lack the reasoning capacity for accurate self-critique. Smaller models frequently hallucinate flaws or exaggerate trivial issues during evaluation. However, as models cross that threshold, they become capable of serving as their own evaluators, establishing self-play loops for safety. Ultimately, constitutional AI shifts the alignment paradigm. Encoding human values as explicit, auditable prompts transforms AI safety from a manual labor bottleneck into a scalable engineering science.